Okay, hello everyone, and welcome to this talk on the structure of solution sets to regular word equations. So I'll start by introducing word equations. So a word equation is an equation where the two terms on either side are words consisting of terminal symbols and variables. So the terminal symbols are the kind of fixed constant parts of the equation, and the variables are the unknowns. And the idea is to substitute the variables for some words over the terminal symbols such that the two words that you get then on either side of the equation become identical. So for example, we might substitute x for the letter b and y for the word ABA, and in that case we get the same word on both sides of the equation. So the substitution x goes to b and y goes to ABA is a solution to this particular word equation. So word equations are regular if each variable occurs at most once on each side. So regular word equations are a subclass of the full class of word equations. And so for example, we can have equations like these. These are regular because each variable occurs at most once on each side, and we don't care what happens to the terminal symbols, A and B in this case. But we can't have something like this where the variable x occurs twice on the left-hand side. So more formally, we have a set of variables x, and usually I'm taking letters from the end of the alphabet to denote variables, and set A of terminal symbols, where I'm usually taking letters from the start of the alphabet, A, B, and C, and so on, to be the terminal symbols. And a word equation is a pair of words over this combined alphabet of variables and terminal symbols. A substitution is a homomorphism from the combined alphabet to the terminal alphabet such that it acts as the identity over the terminal symbols. And solutions are substitutions which equate the two sides. The length of the equation is simply the sum of the lengths of the two terms, and the number of occurrences of a symbol in a word or in a term is denoted with this modulus and subscript, and the set of variables occurring in a word is denoted by this var notation. So probably the most fundamental problem one can ask about word equations is the satisfiability problem. So given a word equation, does there exist some solution to that equation? And there are several algorithms which are known for solving the satisfiability problem. The first one is due to Makanin, was presented in 1977, and since then Plandowski improved this to an algorithm working in polynomial space, and later Yezh introduced the recompression technique, which he's shown recently to work in non-deterministic linear time. So we have this complexity upper bound of non-deterministic linear time, and it's relatively easy to see that the problem is NP hard via reductions to the pattern matching problem, which is known to be NP complete, or to, for example, integer programming, which you can do if you have only a single terminal symbol. Then the problem becomes an integer programming problem. But what remains open is whether or not the satisfiability problem is actually in NP, whether it's NP complete, or equivalently to settle the precise complexity of the satisfiability problem. This has remained open for a long time. So just to give a bit of context then for this subclass of regular word equations, which is the topic of this talk and our paper. So we have the general class of word equations, as I've just said, is NP hard. The satisfiability problem is NP hard and is also can be solved in non-deterministic linear time. We have a couple of cases which can be solved in polynomial time. So if we limit the number of variables to 1, then we can solve this in linear time. If we limit it to 2 variables only, then we can solve this in polynomial time. The degree of the polynomial is 5, I think. Currently, that's the best known. And we also have this case of linear equations where each variable can occur at most once. So we don't limit the number of variables, but each variable can occur at most once in the equation. And this is a relatively trivial case, at least in terms of the sort of complexities that we are looking at. It's trivial to see that it's solvable in polynomial time. We also have the pattern matching problem, which I already mentioned is NP complete, and this is the case when exactly one of the sides of the equation, one of the terms, consists only of terminal symbols. And in this case, if we want to get a solution, then we can't map the variables to something long, because otherwise we'll get on one side a word which is longer than this fixed word consisting only of terminal symbols. And that means the set of sort of viable substitutions which might result in solutions is finite. So that gives us more or less a trivial upper bound of being included in NP, and it's also known that it's NP hard. And as well as that, there's been lots of research more recently into subcases that are solvable in polynomial time, or that with sort of parametrized complexity upper and lower bounds as well. Then we have this kind of strand here. At the top we have quadratic word equations, which are equations for which each variable occurs at most twice. So in that case we still have NP hardness, but we don't know any better upper bound than for the general case. Then the class of regular word equations, which is what I'm going to talk about today, is sort of sandwiched between quadratic and linear equations. So it's a restriction of the quadratic equations, but more general than this trivial linear case. And there are also a couple of other subcases of the regular word equations which have been considered already in the literature. The first is regular ordered. So these are regular word equations for which the order of the variables is the same on both sides of the equation. So if we have each variable can occur at most once per side, that's the regular condition, and they also occur in the same order as read from left to right on both sides of the equation. And this class is, despite being very restricted, is NP hard, and actually it's not too difficult to show that it's also in NP, so it's NP complete. And the other class is the regular reversed equations, for which we have the variables occurring in one order on the left-hand side and exactly the opposite order on the right-hand side. And there we have a rather involved technical proof in a paper at MFCS 2019, which showed that this is actually in NP. So the satisfiability problem for this class is in NP, but we don't have corresponding lower bounds, NP hardness lower bounds in that case. So the regular class of regular word equations then gets NP hardness as a direct result of the regular ordered equations being NP complete, and the main result of our paper and this talk is also inclusion in NP in this case, so complexity upper bounds, which come about as a result of a better understanding of the solution sets to regular word equations. So what's also interesting is to consider the generalized satisfiability problem, where you're given a word equation and some additional conditions or constraints on the solutions, and you want to know whether there exists a solution satisfying those constraints. So as an example, you might have some word equations we have here over the variables x, y, and z, and you want to know whether a solution exists such that the length of the image of x is equal to the length of the image of z, and additionally the variable y belongs to some regular language, for example. Now, there are lots of different kinds of constraints that one might want to consider and that have been considered in the literature. So you have things like regular constraints, so a membership of a variable for a regular language, involution, length constraints, by which I mean linear arithmetic over unknowns which correspond to the lengths of the variables. So there's been a lot of interest in rewriting transformations such as the replace all operator, transducers, morphisms, and also relations from combinatorics on words such as abelian equivalence and the scattered subword relation. Now, regular constraints in involution are known to be decidable, but many of the others, so the rewriting transformations, abelian equivalence and scattered subword and so on, are actually undecidable. But one particularly interesting case is that of length constraints, which has been open now for quite a few years, since the 1980s. And to get an idea of why this is a difficult problem, the sets of solutions to word equations actually can be quite expressive and quite complicated. So suppose we have the equation E given by x a b y is equal to y a b x. Then if we define the set of pairs of non-negative integers n and m, such that there exists a solution to E, and n is the length of the image of x, and m is the length of the image of y for that solution. So these pairs are basically describing the lengths of solutions to my equation. Then it's known from an advert paper 2018 that this set S is actually not definable in Pressburger arithmetic. So the solution sets have some quite high expressive power in terms of the what they can express in terms of numbers, in terms of tuples of numbers. So we need to better understand these sets of solutions in order to be able to address these extended satisfiability problems. And in order to do that, we need to be able to represent them somehow. So in general, the solution sets can be infinite, and we need some finite way of representing them. And one way to do that is using parametric formulas. So for example, we have these equations such as xy equals yx, and we can describe the set of solutions using a formula containing variables, word variables or word parameters, and numerical variables or parameters. And I'm not going to give a full formal definition of what I mean by these parametric formulas and parameterizable solution sets. But basically I want to point out that actually it's known that this is not possible even for regular word equations. So we have an example of a regular word equation for which we can't describe the solution set using parametric formulas of this type. And so we need a more sophisticated method of describing the solution sets in a finite way. And we do this using an algorithm which works for quadratic word equations. It's a folklore algorithm for solving quadratic word equations, which can be used to produce a graph which represents the full solution set in a finite way. So in order to solve quadratic word equations, we first take the step of reducing to non-erasing solutions. So we say that a solution is non-erasing if the variables are not mapped to the empty word at all. And we can reduce to the non-erasing case by simply guessing which variables should be mapped to the empty word and just erasing them from the equation in advance. And we also want to point out a couple of trivial cases. So if we have the empty word on both sides, then this is trivially solvable. If we have different terminal symbols in the leftmost positions of each side, then it doesn't matter what we will substitute the variables for, we will get different words on both sides in all cases, so then we have no solutions. And likewise, because we now consider the non-erasing case, if we have the empty word on only one side of the equation, then we won't be able to get any solutions either. So the algorithm for solving quadratic word equations is centered around this rewriting relation, which in turn is based on transformations called Nielsen transformations. So I represent it by this arrow subscript nt, and essentially it's a relation on the set of quadratic word equations, and each of the rewriting transformations can be associated with a morphism. Now if we can apply a series of these rewriting transformations to our original equation E and reach the trivial equation where we have the empty word on both sides, then composing the morphisms associated with each individual rewriting step in that sequence will yield a solution to the equation. And in fact, all solutions to our original equation can be obtained in this way. So this rewriting relation is going to be able to tell us whether or not the equation is solvable, and also it contains essentially the full set of solutions. Now the first rewriting rule is a basic cancellation rule. So if we have the same symbol in the leftmost position on both sides of the equation, so a variable or terminal symbol, then we can simply cancel it, and we don't change the set of solutions in that case. So we have this rewriting rule belonging to our rewriting relation, and the corresponding morphism in this case is the identity morphism. Now the main rules of the rewriting relation are as follows. Suppose we have an equation where the leftmost symbol on both sides is a variable, and I have variables x and y. Then one of the transformations is obtained by replacing x everywhere with yx, another one with replacing x with y, and another one replacing y with xy. And essentially what will happen there is we get these new equations. We will have increased the length by 2, but we will then get the same symbol in the leftmost position on both sides after having applied one of these transformations. And so we can simply apply this cancellation rule and get rid of them, and then we're left with an equation of the same length again. And the intuition behind these transformation rules is that, so for example, with this case with x goes to yx, then the new equation that we get will have a solution, a non-erasing solution, if and only if our original equation has a solution satisfying that the length of x is greater than the length of y. Similarly, if we replace x with y, then the equation that we get as a result will have a non-erasing solution if and only if our original equation had a non-erasing solution satisfying that the length of x was equal to the length of y, and so on. So we get these splitting of the search space of all solutions essentially by applying these rules. Now, if we don't have two variables but only one variable on the leftmost positions of the two sides of the equation, then it's basically the same, except we lose one case because we consider length non-erasing solutions only. we can't have that the length of x is shorter than the length of our terminal symbol, which will be 1. So we lose one of the possibilities in that case. And we can't have the possibility that we have terminal symbols on both sides. That's already covered either by the trivially unsolvable equation or by the cancellation rule, depending on whether those terminal symbols are the same or not. So this is the rewriting relation that we have, and it preserves the properties of being quadratic and regular. So it also preserves the length or the maximum length, so we can never increase the length, and we never introduce any new symbols. As a result, the set of equations we can reach by applying these rewriting transformations is finite, and we can simply enumerate it. And if we enumerate it, what we can do is we can construct a graph, a directed graph whose vertices are equations which are reachable from our original equation by applying these rewriting transformations, and where the edges are corresponding to the individual rewriting transformations or the morphisms associated with them. Then the equation will have a solution if and only if somewhere in this graph we get the trivial equation with the empty word on both sides. And in fact, all solutions to our original equation will be encoded as walks in the graph from the original equation to the trivial equation. And we can get the solutions by composing the corresponding morphisms, as I said before. Now we have this graph which represents solution sets to quadratic word equations. What we want to do is better understand the structure and properties of these graphs. And that's exactly what we do in the regular case. So in order to try to understand the structures of these graphs, the first thing is to note that we can divide the rewriting transformations into those which decrease the length of the equation and those which preserve it. And then we can divide the graph of solutions into components consisting of the length preserving transformations, so consisting of equations of the same length, and these individual sort of length constant components will be connected together in a DAG-like structure of linear depth, because we can only apply a linear number of these length decreasing transformations, and we can never loop back to an equation of longer length again. So we'll end up with these length preserving components. They can be large and complicated, but when we kind of consider how these individual length preserving components are arranged, it will be in a relatively straightforward directed acyclic graph structure of at most linear depth. So for example, with this graph that we've already seen for the equation xay is equal to yxa, I've highlighted the length preserving transformations in red, and so the length preserving components will be these ones that I'm circling now. And hopefully it's not too difficult to see why these individual components might be as large and complex as necessary, but that they're arranged in a relatively straightforward DAG structure. So it's this length preserving part of the transformation that we're going to be interested in, because the rest of the structure follows in a relatively straightforward way. So if I drop the subscript nt from my arrow notation, then this corresponds to the length preserving part of the relation that we had, the rewriting relation. And this is really the interesting part of the relation for the reasons that I've just said. And actually it's worth noting that if I take the reflexive transitive closure of this restricted length preserving rewriting relation, then this will actually be an equivalence relation, or in other words, these length preserving components of the graph will be strongly connected in the regular case. Now I'm going to use this notation here, the G with the superscript arrow and subscript E, to denote the graph whose vertices are equations E prime, such that my original, I can get to E prime by applying a sequence of length preserving rewriting transformations to my original equation E, and such that the edges basically correspond directly to these individual length preserving rewriting transformation steps. So these graphs G will be exactly the length preserving components in the whole graph of solutions. And it's these individual length preserving components that we're going to describe in greater detail. So the first result that we have is concerning the diameter. This is arguably the most important one. So if we have a regular word equation E, then the diameter of these length-preserving components will be polynomial in the length of the equation. And the way that we achieve this basically is through a pair of reductions, firstly from regular equations to something called basic regular equations, and then from basic regular equations to jumbled basic regular equations. So this is a much more restricted class of regular equations, and in this case we can show that every node in the graph will be a polynomial distance away from some sort of normal form, and there are polynomially many possibilities for these normal forms, which we show using some invariant property introduced for the basic regular equations. And then once we know this fact, we can describe the structure for basic regular equations in quite precise detail in terms of the structure for jumbled basic regular equations. So once we understand the jumbled case, then we know about the basic case, and again, once we know about the basic case, we can describe the structure for regular word equations in general in quite precise terms, in terms of these more restricted basic regular equations. So that's kind of the overall structure of the technical contribution of the paper, and the main end result is that the diameter will be polynomial. And this actually means then that the satisfiability problem for regular word equations is in NP, because if I want to know if this trivial equation with the empty word on both sides is somewhere in the graph, I can just get a path from the root to the trivial equation, and under the assumption that this path is the shortest possible, then I will only ever pass through a linear number of these length-preserving components, and in each one the shortest path must be polynomial in the length of the equation. So overall the path will be polynomially long, and verifying this path by checking that each step really is one of our rewriting transformations is obviously also polynomial, so that I can check that if such a path exists in polynomial time, in non-deterministic polynomial time, once I've guessed it. The second result is regarding size, and in the paper this is actually given more precisely for basic regular word equations, but since I don't define them in this talk, I'm going to give it in the more general case. And essentially we can interpret it as follows. So suppose we have a regular word equation E, and let n be the length of the longest of the two sides of the equation, and let capital V be the number of vertices in this graph G. Then V is upper bounded by n factorial over 2. And in fact, this upper bound is reachable in the case that we have a regular rotated equation. So this is another subclass of regular word equations. And if we have a regular rotated equation consisting only of variables, then we actually will hit this upper bound here. So these graphs can get really quite large. That's the main unfortunate message there. And but they can't get any larger than n factorial over 2. And in terms of lower bounds, in order to get meaningful lower bounds, we need to have some indecomposability result. And so basically that means that we can't split the equation into several smaller ones and solve them separately. And if we have this indecomposability condition satisfied, then we can also show that V is at least 2 to the n minus 1 minus 1, where m is the number of variables which occur on both sides of the equation. So actually in general, if we have again equations satisfying this indecomposability condition, then the number of vertices in these graphs will be exponential, and it will be between these two values. And then finally we considered the connectivity of the graphs, and the reason for this is that if the graph of solutions, so the global graph of solutions, the whole graph, is a directed acyclic graph, then the solution sets will be parametrizable. So we can describe the solution sets using these parametric words I introduced earlier. And as a result, many of these generalized variants of the satisfiability problems, many of these additional constraints will actually become decidable, because we have this more explicit representation of the solution sets. Unfortunately, we usually won't get a DAG, and in most cases we will actually have a graph which has cycles in it. But we can measure how DAG-like the graph actually will be, so how far away it is from a graph, how close it is to the complete graph, using connectivity measures such as DAG width. And what we showed was that there are examples for which the DAG width can grow linearly with respect to the length of the equation, so it's not bounded by a constant in general. However, we also identified some infinite subclasses for which the DAG width is a low constant, so for example 2. And these, I think, are a particularly interesting case because this is sort of one step up from what we know to be a nice class for example, for length constraints. So we know if we have a DAG, then the length constraints, satisfiability problem with length constraints will be decidable. But if we have a graph with DAG width 2, which is kind of one step up from being a DAG, then we don't know whether it's decidable or not anymore. And I think this is a particularly nice subclass to identify and then to work on for the future. So in addition to looking at these examples with particularly low or particularly high DAG width in the context of generalized satisfiability problems, in particular with length constraints, I think that other future work would be particularly interesting to consider the general class of quadratic equations and to see if we can generalize our results to quadratic word equations in general, and also to try and improve our bounds on the diameter. So the polynomial we had there had quite a high degree, and it would be nice to either get some lower bounds and showing that they're relatively tight, or to improve the upper bounds that we have already in that case. Thank you very much for listening.